Thank you, Irina. Good afternoon, everybody. Thank you for attending this conference. I'm delighted to be here to share with you some thoughts about AI hardware, what is next. All right, so we know the four pillars of AI are algorithms, data sets, human talent, which sometimes is forgotten, and hardware. And it is this last topic that I want to talk about. So if we look at the computational effort that has taken in training some of these networks that have demonstrated seemingly superhuman capabilities in the last few years in solving difficult and very interesting problems, you can see how the computation performance has been rising exponentially. That scale on the left is an exponential scale, and this has started about 2012 or so with the advent of GPUs being used in AI computation. You can see how in the last few years, the amount of computation that is used to train some of these models has really increased very sharply. It's doubling essentially every 2 months or so. Now, of course, this comes at a cost. And so if you look at the amount of money that is involved in machine time and also the cost of electricity in training these models is really also rising exponentially and is really reaching now $10 million and beyond. So it's becoming very significant. Now, this chart shows you this plots the other cost that is involved in all this computation, which is the power, the energy consumption that is involved. And so this is a chart that summarizes the peak performance in giga operations per second as a function of the peak power consumption of various AI chips and AI accelerators over the last few years. And you can see how there is this very big trade-off that emerges. Essentially, the slope of a line that emerges there, or that band that emerges, has a slope of 1. In other words, you want more computation, you better be ready to burn more power. You can also see how they span several orders of magnitude. So on the bottom left, you have systems that burn very little power. They're very nimble. They're used for IoT applications. And as you go towards the right, you're throwing more performance at it. You're burning more power. When you get to the top right, you are now looking at cloud systems that are extremely energy hungry, but of course, they also deliver tremendous computation. Now, I want to tell you about that one spot in there. That spot exceeds 10 kilowatts in power consumption, and of course, it achieves tremendous computational efficiency. And I want to tell you about this because as a microelectronics engineer, this is an extraordinary chip, if we might call it that way. This is the Cerebros Wafer Scale Engine 2. And this is an AI accelerator that is used in an AI supercomputer, as you see in the picture in the bottom left. That actually is one chip per 300 millimeter silicon wafer, which is the standard wafer fabrication in the world today. So each wafer produces one chip, and this chip has, let me read it here, 463 centimeters squared of area. It's truly extraordinary in size. It has 2.6 trillion transistors and 850,000 cores and 40 gigabytes of on-chip memory. It's fabricated by TSMC in one of their most advanced technology nodes, which is the 7 nanometer node. So this gives you a sense of how far things have gone in really pushing microelectronics to the limit in order to achieve the kind of computational performance that we have seen before. Now, of course, concern has been mounting, as you know very well, about all the great things that AI can do, but let's hope that it doesn't burn the planet along the way. So there is really tremendous interest in finding a way to continue this progress, the rate of progress, but doing it in a far more energy efficient way. And so if we come back to this chart, what all those chips and AI accelerators have in common is that they are all fabricated using modern CMOS, complementary metal oxide semiconductor technology. This is the standard technology today for silicon microelectronics. There are different chip classes. There are CPUs, central processing units, GPUs, graphical processing units, FPGAs, ASICs, different architectural designs, different trade-offs in terms of time to market, density, power performance, etc. But they all are made by CMOS, by standard CMOS in different nodes, meaning different levels of advancement. And so what you can see is that there is a fundamental trade-off, which is the top of those three lines that are crossing that band, which is about 10 teraops per watt. And that's as far as CMOS essentially will do. You can go up and down this slope, but it's very hard to go beyond. As you can see, there's almost no data beyond. So the hardware challenge is how to go beyond. How could we increase the performance per watt ratio by orders of magnitude, which is what is going to be required to do justice to all the great work that is being done in algorithmic development and in data sets. And so it is here that I would like to speculate on a couple of paths forward that are being investigated around the world that are looking promising, also including MIT. Now, one of the elements is to mitigate what is known as the memory bottleneck, and the second one is new computational approaches, which I will give you some idea. So what is the memory bottleneck? So it turns out that the silicon technology that is used to implement processors, where you do the computation, and to implement the memory, where you hold the data, is actually very different. And it's very difficult to have one silicon chip that contains high-performance logic and at the same time high-dense, inexpensive, fast, energy-efficient memory. So as a result, these chips are actually made by different technologies. They are separate from each other. And as you can see on the graph on the left, they are mounted side by side on a board. And what that means is that there is going to be some metal lines that connect these two chips, which are going to be of a certain length and of a certain size. And as a result, this is going to introduce a certain amount of latency in the time that it takes the data to flow from memory to the logic chip and then back again, and also is going to consume quite a bit of energy in order to drive these lines and do all this. And so this is today the bottleneck to the enhancement of the computation efficiency, both in performance and in energy consumption. Now, the solution is sort of obvious. Well, let's just try to bring memory and compute together. As I said earlier, the technology, the underlying silicon technology is just far too different to make this possible at this time. But what we can do is more intimately bring these two chips together through a packaging process so that we have them right on top of each other, as the graphic on the right indicates, connected with a very high density of very short vias that provide data at a very high throughput and burning very little energy as you get the data back and forth between memory and compute. And so one approach to do this, which is now being seen as a true revolution incoming, is what is known as heterogeneous integration of chiplets. And this applies beyond just AI engines. This really applies to all kinds of complex systems. So on the left, you see the classical approach. This is a monolithic chip. It's a one-chip solution, a system on chip, that contains a number of functions in it. In that chip, you see CPU cores, communications, memory, graphics, input, output, etc. You need all this for this system to function. It all has to be put together in this one chip. And as a result, you can only use one CMOS technology, one type of technology that is going to be used to make that chip. So that forces you to make a number of compromises. Typically, the CPU and the graphics require very high performance. So you are going to use your latest node that you have access to implement those functions. But you're now stuck using that latest node, which is expensive, to all the other functions, which in many cases is not an optimal thing to do. So you end up with a solution that is inflexible, because you have to use this technology for all functions, and that is quite expensive, because you're using expensive technology to do functions that could be done in a cheaper way. So on the right, or rather towards the center, you see the new approach, which is a heterogeneous integration of chiplets. So here you now have the different functions that you are going to need to make your system work implemented using different chips. These chips only do one function. They are smaller, which means that the yield is going to be higher, and as a result, they're going to be cheaper. But furthermore, they are now made with a technology that is optimum for that function. And that is going to give you a better performance in terms of energy, cost, etc. And what you do then is you find a way to integrate all these chiplets together in a very compact way, in a very energy efficient way, with very, very short distances in a very energy efficient way. So this is the new approach that is being conceived to create systems that is also going to have a very significant impact into future AI systems. By the way, all those chiplets, you could have a bunch of them that are already off the shelf. They're standard, you know them well, and you might only need to design one or two, and so you can also put a system together very quickly. Now, here's an example of an Intel microprocessor that has been released recently. This is called the Ponte Vecchio. It contains 47 chiplets, and altogether 100 billion transistors in one very compact package. And on the right, I'm showing you a report from In-Q-Tel, which is a venture capital firm that supports the US intelligence community, that has declared this technology, the microelectronics industry is on the verge of a very significant change. We're really at the beginning of a new microelectronics revolution of tremendous significance going forward. Now, looking in a completely different direction, another way to enhance energy efficiency is to altogether move away from digital systems into analog systems. This has been studied now for quite some time, And there are projections here that suggest that if you do AI training in the analog domain using resistive elements that you can program that perform, that you mount them in a network, and using Kirchhoff's law and Ohm's law, you can do the matrix multiplication function and the atom function that you need for AI computation. You can do this in a very compact way. Instead of using 100 transistors, you have one resistor to do the job. The footprint is very small, the energy efficiency is significantly enhanced, and the latency is also greatly enhanced. So I'm showing you on the right 2 examples of analog programmable resistive devices that we're actually investigating in my group today. One is a Protonic electrochemical Synapse. This is being investigated with colleagues from the Nuclear Science and Engineering Department, Bige, Yildiz, and Julie, and this is funded by IBM. And this is essentially like a nano battery that moves protons in a controlled fashion. So the protons can be moved from a reservoir into a channel. When they move into the channel, they dope the channel and they change the conductivity. And if you keep the protons there by removing the voltage, they'll stay there, and the conductivity has been changed to any value. And you can draw back, you can take the protons back by changing the polarity of the voltage. So you have a programmable resistor in that way that is non-volatile. On the bottom, you see another approach that we are also investigating, which is a ferroelectric device. It's based on the fact that ferroelectric materials have a polarization state that you can change, and they will hold in memory. And if you have a multi-grain material, then you can selectively change a few of the grains, the polarization of a few of the grains, in a controlled fashion, and again achieve a linear programming of the resistor, which is read by a semiconductor channel underneath. These are 2 examples of analog hardware. And then one, looking even beyond in terms of novel concepts, I'm showing you here an example from colleagues here at MIT, Dirk Englund and Marin Soljacek, of a matrix multiplication engine that is done through passive linear optics. This is a massive parallel system, all in the optical domain, that has the potential for also very energy efficient and very fast AI model development. So all this this work has shown to us that this is really an extremely strategic and interesting area for us to work on. And so I'm happy to announce today that we are launching at MIT a program that we call the MIT AI Hardware Program. In fact, the inaugural symposium is actually taking place tomorrow, which is an academia industry initiative that is dedicated to advance of the next generation artificial intelligence hardware. And this has to be an academia-industry collaboration because, in academia, we love to work on interesting problems, but at least at MIT, we not only want to work on interesting problems, we want to work on relevant problems. And so this is where we get the guidance from our friends and collaborators in industry to tell us which problems are interesting, but also which problems, if we solve them, make a contribution to humanity. So these are the companies, the inaugural set of companies that support this program. As you can see, these are companies that come from very different walks of life. If you are interested in knowing more about this, you can write to me or my colleague, co-lead of the program, Odd Oliva, who is also here, and we'll be happy to tell you about the program. And with this, I'll be happy to take your questions. Thank you. Absolutely. The question is whether there is a role for federal or state government to advance the energy efficiency of AI systems. Yes, as I have tried to hint in this very short talk, there's a lot of fundamental research to be done. Research that is pre-competitive, is way before eventually reaching the marketplace, and that is best funded through the government, through programs that really emphasize developing fundamental understanding and developing fundamental technologies. Without it, it would be a much longer slog to develop those technologies. How mature is the technology for analog computing devices? Well, there's a lot of research around the world in many different device approaches. I've shown you 2 that we are working on in my lab, but there are many others. And the demonstration of arrays at different dimensions. I think the consensus at this point is that there is no one analog device technology that meets all the requirements that are understood and required for these arrays to perform their function in an efficient and fast way. So the research towards identifying that ideal device or something that approaches to an ideal device continues. And so, yes, there has been a lot of progress, which gives us impetus to continue this research, but we need to continue the research to find the ideal device and the ideal material system. What's a realistic time frame for no traditional architectures, e.g. optical or analog? Well, I've been in the microelectronics business for a long time, and I have seen consistently throughout my career that it takes about 10 years for a new technology to reach the marketplace. So typically a new technology will be presented at a major conference or will be published in a paper, and so you have an early result that looks very promising. From there until that technology shows up in the marketplace is typically 10 years. In some cases, it takes actually more than 10 years. So frankly, I don't see how we are going to do any better than that, considering that we are really talking here most likely about new material systems based on new physical principles. So we have to be engaged for quite a bit of time to make this happen. But we've done it before, so we can do it again.